This is mock AP exam number 1. This is the extended problem that I made to be 25 minutes long. Let me read the problem here. Let f be a differentiable function, so smooth curve, no sharp turns. The table gives values of f and its derivative. So we have our function for f of x, order pair, as well as the slope at each of their points. We have a different function, g of x, that's defined as sine of 3x minus e to the cosine 2x. Another function, h of x, being the integral from 6 to x of j of x, and this is referring to this right here. Okay. All right, so part A, is there a value of c when x is between 1 and 5 such that f double prime of c is equal to negative 3/4? Provide an explanation for your answer. So we want to guarantee a slope off the f prime graph, off the f prime graph. So we're told that f is a differentiable function. It's a function that is at least 2 degrees or higher in terms of its degree, in terms of its x squared or higher. And so we're going to be applying mean value theorem, but we're going to have to adapt our mean value theorem so that it can work for this case. Recall that the point of mean value theorem is to guarantee a specific slope. So if I'm given order pairs for f of b and f of a, or my f of x, I can guarantee a slope off the f of x graph by setting f prime equal to the slope between the endpoints. Now we can also take this and adapt it one derivative down, meaning that if I want to find if I want to guarantee a second derivative value, I can take the slope between the endpoints of f prime and achieve that as well. So if we want to guarantee f double prime is equal to negative 3/4, or if we want to see if this can be guaranteed, we can apply for using the f prime, starting with f prime. So we can say f prime of 5 minus f prime of 1 over 5 minus 1 and see if this results in negative 3/4. If it does, then we can guarantee that there's a second derivative value of negative 3/4 because the points between the f prime graphs produces that particular slope. So f prime of 5, we look at our graph, we look at our table here, f prime of 5 is negative 2, f prime of 1 is 1, so negative 2 minus 1 over 5 minus 1, that does reduce to be negative 3/4. So by mean value theorem, since f prime is continuous on the closed interval and differentiable on the open, then there's a point where f double prime is equal to negative 3/4. Okay. Part B, let k be the function defined by k of x equals f of j of x. Write an equation for the line tangent to the graph of k at x equals 2. So if we want to find the tangent line equation, we first have to find order pair and we have to find slope. I'm going to see if I can get to the slope information first. So if I want to find the slope, I need to find the derivative. To find the derivative, we need to recognize this as a function within a function. We have to rely on chain rule to help us arrive at the derivative. So if we recall chain rule being outside function and inside function involved, we take turns with each of their derivatives. We take the outside function's derivative first, followed by the inside function's derivative. So let's adapt this for this particular problem. So f of j of x, chain rule here, we do the outside derivative, so f prime of j of x times the inside function's derivative times j prime. Replace every x with 2, and then let's see if we can work our way down to a numeric value at the end here. So j of 2 is just going to be negative 1 because we look at our j of x graph. So j of negative 2, or j of 2 is going to be just negative 1. That's the order pair. All right. And j prime of 2 is asking for the slope of the j graph at 2. So the slope of the j graph at 2, it's part of a line segment. So if we just pick 2 points on this line segment and we do rise over run, we do negative 2 over 1. That's a slope of negative 2. So we can put replace j prime of 2 with negative 2. And then we found j of 2, but j of 2, which is negative 1, is still stuck inside this f prime of negative 1 expression. So f prime of negative 1, we go to our table here. F prime of negative 1 is going to be negative 3. So finally, we're down to two numeric values. We can combine those together. Negative 3 times negative 2 is positive 6. So that's our slope. But we still need our order pair. So we're going to plug 2 back into this original equation and see if we can make our way down to the y value. So we say since k of x is equal to f of j of x, k of 2 is equal to f of j of 2. J of 2, again, is negative 1 because that's just the order pair on my j graph. Right? And then f of negative 1, we look at our table, it's just going to be 4. So that's our order pair. Our order pair is x, y, our xy value are 2 and 4. Our slope is 6. So once we have our order pair and our slope, we can dump that into point slope form, and that's our tangent line equation. Part C, find the slope of the tangent line to the graph of g at x equals pi. So if we want to find the slope of the tangent line, we need to find the derivative, and from the derivative, we evaluate the derivative at that point. So we are starting with g of x. Let's first find the derivative. We have to go through chain rule here. Sine of u becomes cosine of u times u prime. E to the u becomes e to the u times u prime, and then there's another chain rule that goes on here. Cosine of u becomes negative sine of u times u prime. So we have quite a bit of kind of nested chain rules going on within our problem. So here's our equation. We're going to find the derivative. Sine of u becomes cosine of u times u prime. E to the u becomes e to the u times u prime. So we need to find the derivative of this full cosine 2x, and this full cosine 2x's derivative is just negative sine of 2x times 2. Okay, we clean this up. We can, well, we don't necessarily clean it up. We just have to be able to plug in our pi. So once we have our derivative, we're going to evaluate the derivative at a point. So plug pi in for all the x's and see if that will get us down to a number. So cosine of 3 pi, that's just going to be negative 1 times 3 is negative 3. E to the cosine of 2 pi. So cosine of 2 pi is just going to be 1. So e to the 1 is just e. Sine of 2 pi is 0, so that's going to wipe everything out. This times 2 times 1 is just going to be 0. So all this goes away. I'm just left with this negative 3. So that's my slope at pi for this g graph, negative 3. Okay, part D says find h of 4 and find h prime of 4. So h of 4 is just using this equation here, replace every x with 4 and see if we can use the graph to help us out. So h of 4 is just the definite integral from 6 to 4 of j of x dx. But notice that for this graph, we're kind of reading backwards a bit. So I'm going to flip that around, make it integral from negative 4 to 6 with a negative in front. And so the definite integral of j of x dx from 4 to 6, we see that we have a triangle here. We're just concerned about the area here. So 1/2 base times height, that's a triangle. 1/2 2 times 3, that's 6 over 2, which is 3. So that's going to give us 3, but then there's a negative that needs to carry over, so that will give me a negative 3. The second part is find h prime of 4. So h prime of 4 is asking for the derivative first. We need to find h prime of x first, and then we can plug in 4. So h prime of x is just I need to find the derivative of this, which I can use second theorem. Right? The derivative of a definite integral. These two notations cancel out. The only thing left over is this upper bound gets plugged into the variable times the upper bound's derivative. So really h prime is just this j of x graph. So h prime of 4 is just j of 4, and j of 4 is just the order pair off the j graph. J of 4 is just going to be 0. All right, part E. On what interval is our graph of h increasing and concave down? So this is our h function defined here, and then this h is related to the j of x, but h is the definite integral of j of x, which means that I need to, which means that in order to make j of x and h of x equal, we have to push a j of x through the antiderivative form or method, which means that this j of x is really sitting at the h prime level, right? And so if we think of this as an h prime graph, we can really think of this as a derivative graph, and from there we can gather information about where the graph is increasing, where the original h graph is increasing and decreasing, and also we can pick out peaks and valleys to help us determine information about concavity. So I labeled my derivative graph. Anything above is positive slope, anything below is negative slope, anything on the x-axis is slope of 0. So my critical points is going to be 1.5, 4, and 6. Okay, and regions above the x-axis represents positive slope. So my original h graph is going to be rising in this interval, then it's going to fall, and it's going to rise again. I also want to gather information about concavity, so I'm also going to create second derivative sine lines. So the way we can pick those off, critical points are going to be the peaks and valleys. These are going to be points of inflection. And anywhere that my derivative graph is rising will indicate where my original graph is going to exhibit concave up. So concave up from 0 to 1, concave down from 1 to 3, concave up from 3 to 5, concave down from 5 to 6. So I have my sine lines for h prime and h double prime, and I'm just trying to match them up, trying to match my stack my two h prime and h double prime sine lines and see where I'm going to get both those properties to show up. I want increasing and concave down, so increasing and concave down, that's going to be in this interval here from 1 to 1.5. And then increasing and concave down, again on this interval from 5 to 6. All right, part F. Find the absolute minimum, absolute max on the h graph from 0 to 6. Justify your answer. So the absolute max and absolute min, this is applying extreme value theorem. So extreme value theorem means we need to test the endpoints and we need to test the critical points. And those critical points and endpoints come directly from the h prime sine line. So we're going to test h of 0, h of 1.5, h of 4, h of 6. And the definition that we're going to use is this h of s graph. So we're going to find all those critical values by plugging into this form. So first up is 0. So 6 to 0. I would prefer to read the graph from left to right, from smaller to larger. So I'm going to flip the bounds and change that sign. And then I'm going to add up all the values that I see from 0 to 6. First up is understanding that these are all triangles. We fill all those regions in with areas of their respective triangles, and then making sure that we keep track of positives and negatives. So positive 0.75 in this region, negative 3.75 in this region, and then 3 in this region. So we combine that up to get 0. The integral from h of 1.5 is the integral from 6 to 1.5. We flip those bounds there, and we total the regions up, and we get 0.75. h of 4, flip the bounds, change the sign, and we get negative 3. h of 6, the bounds are the same, so it's just 0. So we compare all these values here and see which one is the highest and which one is the lowest. The maximum value that we see is 0.75. The lowest value that we see is negative 3. Okay. All right, one more to go, and that's part G. Evaluate the definite integral from 1 to 3 of f double prime of 2x dx. So f double prime of 2x, we really want to go through u substitution to get this in a better form here. So let's replace, let the u value be 2x. So du equals du over x is equal to 2. We solve for dx, dx equals du over 2. We make our substitutions. Okay, we're going to go ahead and replace replace the 2x and the dx. And when we do that, we can convert it to be in terms of u. And then we can push that 1/2 out in front. So the definite integral of f double prime of u, we don't have anything available for f double prime, but we can apply the first theorem, which is saying that the antiderivative of f double prime will push this up to an f prime level. So integral of f double prime turns into f prime with the 1/2 out in front. Okay. Let's replace the u back in terms of x, plug in our upper and lower bound. So we get 1/2 f prime of 6 minus 1/2 f prime of 2. Now we have something that we can use because we have information regarding f prime, so now we can find those values. F prime of 6 is 2, f prime of 2 is 3, and reduce that to be negative 1/2. Okay, the other option is we don't have to bring this all the way to 2x, although I do think that may be the easier path to go. We could leave this in terms of u, okay, and then plug in our bounds in terms of u, but if we do that, we got to convert the bounds, because what we don't want to do is we don't want to use the f prime of u and then use the 1 and 3. Then we have a mismatch in variables. So either we convert everything to be in terms of x, or if we want to leave this in terms of u, we need to convert the 1 and 3, which are right now in terms of x. The bounds are in terms of x. We got to convert it to be in terms of u. So the way we do that is we look at the u equals 2x. That's the conversion that we use. Plug 1 in for x, plug 1 in for x as well, and then those are going to. Then we can find the corresponding u values. So the 1 will turn into a 2, the 3 will turn into a 6. Now we have matching variables. Now we can plug in 6 in for u, then plug in 2 in for u. We're going to get the same result, use the same table of values to get our same answer.